Hello, welcome to Chapter 10, Part 4, Conservation of Energy. Let's start by taking a look at a device called the pendulum. It's basically just a mass on a string that swings back and forth. But what we're going to focus on here is the energy of this pendulum as it goes back and forth. So when it starts over here at the top, it comes to a rest basically at each end. So we know that the kinetic energy is zero then since it's not moving. And since it's off the ground or the floor here, it has potential energy. So all of its energy here at the ends is potential energy. And then when it swings down to the bottom here, it's lost all of its height or elevation. So it doesn't have any more potential energy. But what it has here is kinetic energy since it's moving. And what's interesting about the pendulum here is that as it swings back and forth, we can see that whatever potential energy it starts with over here, when it goes through and all that energy then becomes kinetic energy. And then over here, it's potential energy again. And by the time it gets back, it comes back to the same position. So meaning that the pendulum has not lost any energy. But what has happened is the energy of the pendulum has been transformed to different types. In other words, it's gone from potential energy to kinetic energy here, back to potential energy, kinetic energy, and then finally returns to potential energy. So this is an example of what is called the conservation of energy principle. It can be stated a couple different ways. The first way is that energy cannot be created or destroyed. It can only be converted from one form to another. Another way of saying this is that the total energy of an isolated system is constant. So remember this term conservation in physics means that the conservation of energy means that the amount of energy is conserved, which just means it doesn't change, it's constant. However, what we see in this demonstration here is that even though the amount of energy is the same, the type of energy is constantly changing. So energy can be converted from one form to another. It just can't be created or destroyed. So this conservation of energy principle is arguably one of the most important and fundamental laws in all of physics. There's a nice way to sort of visualize the conservation of energy, and that is thinking about buckets of energy. So this is a model to think about how energy is converted from one form to another without losing any energy. So let's assume that we start here with our pendulum over here, and we're going to hold this mass here and then release it so that it can swing back and forth. So when this pendulum first starts, it's not moving, it's at rest. But it has a height off of the ground here, so it has potential energy. So we can think of the potential energy bucket here as filled with energy, okay? And let's say, just to put some numbers here, let's say we start with 10 joules of energy in this pendulum. Our kinetic energy bucket here is empty. In other words, there's no energy in this compartment here. What happens as the pendulum starts to swing down is it starts to lose potential energy because it's dropping in height. However, it's speeding up because its velocity is increasing as it falls and swings. So what this means is we're taking some of this energy out of this bucket and we're pouring it into the kinetic energy bucket. So when it's halfway down, each bucket is half filled and there's 5 joules of energy in each bucket. As the pendulum keeps swinging to the bottom, we take this remaining 5 joules here in the potential energy bucket and we pour it into our kinetic energy container. So now at the bottom, what the energy model looks like is there is no potential energy left. All that energy has been transferred into the kinetic energy bucket here. And then as the pendulum starts to swing up, we start to take this energy here, remember there's 10 joules here now, and we start to pour it back into the potential energy bucket. So at some point here halfway up, we're at half and half. The buckets are each half full. And then finally, when the pendulum reaches its maximum height over here, it stops momentarily before it starts swinging back. And at that point, all of the kinetic energy has been poured out into the potential energy bucket, and we're back into, to this state that we started from. And then this, continues, it goes on and on. Now, one thing we could mention here is that, we said that energy is conserved for an isolated system. And what that means is that no energy is coming into or leaving our system. Now, if we did this experiment, in like a laboratory and watched a pendulum swing back and forth, we would find that it would swing, like this for a while, but after some time, the swinging amplitude here would become less and less. And so the pendulum would start to lose energy, basically, right? It's this arc here would become diminished and energy would be lost. Now, the question is, where is that energy going? And are we violating the conservation of energy principle? Well, the answer is no, we're not violating it, because what's happening here is there are some loss mechanisms, including friction. The string might be rubbing up here, and mostly wind resistance or drag. And what drag does is it transfers energy from the pendulum into the air around it. Because remember, drag is a bunch of, it's due to all the air molecules slamming in to our mass here as it plows through the air. So those air molecules now are receiving energy. It's like, this is like swinging a baseball bat and knocking all those air molecules around. So what's happening is the energy is being transferred from the pendulum into the room as thermal energy, okay? And so to make this, energy model more accurate, we could add a third bucket over here called thermal energy. And therefore, every time it swings, we would be transferring a little more energy into that thermal energy bucket. So if we consider the entire room or laboratory as our closed system, then energy still is conserved. Once the pendulum, loses all its energy, well, that energy is not destroyed, it's just transferred into thermal energy. The conservation of energy principle is a really important one for solving problems, and it's a really good way to solve a lot of physics problems that is provides a more efficient and elegant solution compared to doing some of the other methods that we've seen using kinematics and dynamics with Newton's laws and so forth. So this is going to be a powerful tool for us to solve a lot of problems. So we want to come up with a way to quantify the conservation of energy principle. So what we're going to deal with here is the conservation of mechanical energy. Remember, mechanical energy means kinetic and potential energy. So the idea here is that energy is not lost or gained in an isolated system. So the initial total energy of our system is equal to our final total energy of the system. So we can write this as E total I for initial, is equal to E total F for final. So the total energy is equal to kinetic plus potential energy. So K for kinetic, U for potential, and again, the I here is for initial, and then over here we have final kinetic and final potential. Furthermore, remember that kinetic energy is equal to 1/2 mv squared. This is the initial velocity, v sub I, and then if we're talking about gravitational potential energy, this ui is equal to mghi, where hi is the initial height. And then on the right side, we have the final kinetic energy is 1/2 mv final squared plus gravitational potential energy, mgh final. So this is a statement then, if there is just gravity involved in motion, this is our equation for the conservation of mechanical energy. Now, we can add more to this, though. We can make this more general. What if, for example, springs are involved in the system? Then we have to include elastic potential energy as well. So starting with this equation here, all we have to do is add the terms for elastic potential energy. So and this is U, where the S is for spring, and then I is for initial. So remember, for a spring, for elastic potential energy, the potential energy is given by 1/2 kx squared. So xi, this is the initial displacement of the spring. And then over here is the final elastic potential energy, 1/2 kx final squared. So now, our equation is starting to get a little more messy and adding more terms. In fact, we're going to even go a little farther. Let's see what happens next. So the previous slide dealt with conservation of mechanical energy, but what if there's friction present? Well, we can modify our law on the previous slide to include losses due to friction. So once we add that, this equation here, which is quite a handful here, can be used for any type of energy that we're going to use here in Physics 101. So what we've done in this slide is we've taken the result from the last page, which were these 6 terms here, and we're adding one more. We're adding the change in thermal energy due to friction in the system. Okay, so with our pendulum, for example, this would be the energy that is lost, by the pendulum and becomes thermal energy in the room. And we'll see other examples where we use this. So remember, the change in thermal energy is equal to the work done by friction. Right? We talked about this in one of the earlier parts of this lecture. So we have the kinetic friction force, F sub k, times the distance that friction works over. That's the displacement delta x. So, again, there's sort of good news and bad news here. The bad news is this is a, almost ridiculously long equation, right, with a lot of terms. There's 7 total terms here. So that's kind of scary. The good news is that in almost all the problems that we'll deal with, we will not have all these types of energy. In other words, over here, the initial types of energy, it may only be one type of energy. And over here, the final types, there may only be one or maybe 2 types of energy. So that will simplify this equation significantly. And this will become clear as we work through several examples. So the rest of this lecture now, I'm just going to go through a whole bunch of examples because that is the best way to learn about how to use conservation of energy principle. Let's get started with our first example. How fast is a 10-kilogram rock going when it drops 100 meters to the ground? Well, so this is one of those problems where we could solve it several different ways. We've seen how to do this with using kinematics, using dynamics. We even saw how to do it using the work energy theorem. So now we're going to solve it using the conservation of energy principle. And this is probably the simplest and most direct way to solve a problem like this. So let's think about this situation. We've got a rock that starts up here 100 meters above the ground, and we release it and it falls down to the ground. So let's think of this from an energy standpoint. What type of energy does the rock have up here at the top? Well, it only has potential energy because before we release it, there's no motion, right? So there's no kinetic energy. So the total energy up here is mgh, where h is the height of the rock. Now, the rock falls, and we know that potential energy gets converted into kinetic energy as it falls. By the time the rock gets down here, right before it hits the ground, it's lost all of this potential energy, and it has only kinetic energy, right? Because the rock has no height now, so h is 0. So the total energy of the rock is given by its kinetic energy, 1/2 mv squared. So conservation of energy principle says that the initial energy up here has to be equal to the final energy down here. So we just set these two things equal to each other. So in a sense, we could start this problem just like this. We could just say mgh equals 1/2 mv squared. And the nice thing about doing this is we see the answer we're looking for right here. Here is the final velocity of the rock. All right, we've already got the velocity right there, and now all we have to do is a little bit of algebra to figure it out. One thing you can do immediately is notice the masses, m's, cancel. So we can cancel those out, and we get this result here. We multiply by 2 to get rid of the 1/2, and we have solved for v squared. And then to solve for v, we just take the square root of our result. So we have the square root of 2gh, g is 9.8, and h is the height of the rock in meters, which was 100 meters. So this comes out to be 44.3 meters. So this is, again, using conservation of energy here, we can start this problem right here by just saying that the initial potential energy of the rock, mgh, is equal to the final kinetic energy of the rock, 1/2 mv squared. And, we see our answer as the velocity right there. So it's only a couple steps to solve this problem. For our second example, let's ask the question, how high does a 2 kilogram rock go if you throw it at 25 meters per second straight up? And then also, how fast is it going when it comes back down? All right, so the first thing to do here, again, is to make a little sketch here of what's going on. So now the rock is going to start down here. This is sort of just the opposite of the last problem we did. The rock starts at the bottom. So the initial energy of the rock is kinetic energy because the rock has no height yet, right? We're assuming that we're throwing it right from the ground. So the total energy of the rock initially is 1/2 mv squared. When the rock goes up and reaches its highest point, it stops and then of course starts to fall back down. So at its highest point, the rock has no kinetic energy because its velocity has reached 0. So it has only potential energy in the final picture up here. So the energy of the rock is mgh. So once again, we can equate these two terms here. The initial energy of the rock down here has to be equal to the final energy of the rock up here because of the conservation of energy principle. So again, we can just equate these two terms here, and this time we're going to solve for the height. So we have mgh equals 1/2 mv squared. We're going to solve for h. So again, the masses, notice they cancel out. We can divide by g to get rid of the g in front of the h. And here's our answer. The height is the velocity squared divided by 2g. So we can plug in our numbers. Velocity is 25. Remember to square that. And divided by 2 times 9.8, that'll give us a height of 32 meters. So again, this is a much more straightforward way of solving this type of problem than using the equations from projectile motion that we talked about earlier in the course in chapter 3. This is a real quick, it's just a couple steps here to find the height of this rock. Now, let's think about this problem a little further. How fast is the rock going when it comes back down and hits the ground? So the rock starts down here, we throw it up, it gets to this position here at 32 meters, and then it turns around and it falls back down. So we're trying to figure out how fast is it going when it reaches the ground again. Well, there's an easy way and a hard way to solve this problem. The hard way would be to go back to the previous example and redo that problem for an initial height of 32 meters. But we don't have to do that much. The simple way to solve this problem is to use conservation of energy. If this rock doesn't lose any energy, right, it goes up and it comes back down. If it has to have the same energy everywhere, then when it comes back down, it's got to be going just as fast as it went up initially. In other words, if we throw it up at 25 meters per second, when it comes back down, it's going to hit the ground at 25 meters per second. Why? Because the energy at the bottom is all kinetic energy, and the energy has to be the same, right? Energy is conserved. We're assuming no energy is lost here. We're ignoring wind resistance and drag and so forth. So by conservation of energy, it'll have the same speed when it hits the ground. Here's example number 3. You're riding home on your bicycle at 12 meters per second when all of a sudden your chain snaps, meaning you start coasting. Your house is at the top of a 10-meter hill. Can you coast to your house? Ignore wind resistance and friction. So here's the picture of what's going on. You're riding your bike along here on a flat ground here at 12 meters per second, and your chain breaks. So you can't pedal anymore, right? So all you can do is coast. So you're going to try to coast up this hill to your house which is at an elevation of 10 meters above the ground where you started. So this is a good example of using conservation of energy principle to solve this problem. We know that the initial energy of the bike here is all kinetic energy, right? Because the bike is on the ground at, an elevation of 0. There's no height, so there's no potential energy. So the energy of the bike is 1/2 mv squared. When the bike goes up the hill and gets to, let's say it, gets to this point right here, well, then you're going to slow down and come to a stop. So we're going to try to find out how high you can actually get. So at this point where your bike coasts to a stop, you don't have any kinetic energy anymore. Your energy is all gravitational potential energy. So the final energy, E final, is equal to mgh. Okay, so now this looks just like the previous problems where we have 1/2 mv squared equals mgh. And what we're going to solve for here is the height. How high up will the bike coast? So again, the masses cancel out, and we end up with this relationship here, and we can divide by g, so that h is equal to v squared divided by 2g, and this time the initial velocity was given as 12 meters per second. So we have 12 squared, which is 144, divided by 2, and g is 9.8, so that's 19.6 on the bottom. So the answer here is 7.3 meters. So what that means is at this speed, you only have enough speed to coast up to right about here at 7.3 meters above the ground. Notice the house, remember, is 10 meters above the ground, so therefore you did not make it to the house. You would have to be going faster to coast all the way up the hill. Our fourth example is a classic roller coaster problem. There are lots of roller coaster problems in physics, particularly when we're dealing with the conservation of energy principle. So in this one, we have a 500 kilogram roller coaster moving at 20 meters per second at the top of a 50-meter hill, and we will ignore friction and air resistance. So here is the situation here. The roller coaster up here, notice, is not at rest. It's moving at 20 meters per second. And it's also at the top of this hill, which has an elevation or a height of 50 meters. Now the roller coaster is going to go down this hill. So there's three parts to this. The first question is, how much energy does the roller coaster have at the top of the hill? So let's answer that one first. Well, we have to look at the roller coaster here and think about what types of energy does it have. So we ask ourselves, is it moving? And the answer is yes, of course. So it's got kinetic energy. The other question we ask is, does it have height? And the answer there is also yes. So it has potential energy. So the energy of the roller coaster is 1/2 mv squared, that's the kinetic energy, plus mgh, that's the gravitational potential energy. And we can fill in all the numbers. The mass of the roller coaster is 500, the velocity is 20, mass again here is 500 kilograms, g is 9.8, and the height is 50. So doing the math here, we end up with a total energy of 345,000 joules. Now part B says, how much energy does the roller coaster have at the bottom of the hill? So the roller coaster is going to accelerate down this hill and get to the bottom. The question is, how much energy does it have down here? Well, don't overthink this. We can use the conservation of energy principle and say that the energy at the bottom is equal to the energy at the top. So our answer, we already found that. It's 345,000 joules. The last part, how fast is the roller coaster going at the bottom after coasting down the hill? So obviously this roller coaster is going to pick up speed as it coasts down the hill. What it's doing is it's transferring its potential energy into more kinetic energy, okay? So we know what the energy at the bottom of the hill is, right? It was 345,000 joules. And the energy type at the bottom is all kinetic energy. There's no potential energy down at the bottom here because the height is 0. So our energy equation just says that the total energy of the roller coaster is equal to 1/2 mv squared, and all we have to do is solve for v. So we multiply everything by 2, divide by m, and then take the square root, okay, and we can fill in our numbers here. The energy at the bottom, remember, was 345,000, and the mass of the roller coaster was given as 500 kilograms. And then remember, this whole thing is square rooted. So this turns out to be 37.1 meters per second. And this answer makes sense. Remember, the roller coaster was going 20 meters per second up here. As it goes down the hill, it picks up speed because it's gaining kinetic energy. So it ends up going faster at 37.1 meters per second. Our next example is one that includes elastic potential energy. We haven't seen this yet in our examples. So we have a toy dart gun. Has a spring with a spring constant of 500 newtons per meter. The spring is pushed in 5 centimeters to load the gun. The dart's mass is 10 grams. How fast does the dart fly out of the gun? So here's a picture of our dart gun, and here's a spring, and the way this thing works is you push this dart into the gun and it compresses the spring. So the spring now has stored elastic potential energy. Where is that energy going to go? Well, when you pull the trigger and release the spring here, the spring is going to push on this dart and make it fly out of the gun. So basically, this elastic potential energy is being converted into kinetic energy of the dart. So this is another example of conservation of energy. There's no energy lost or gained in this system. The energy stored in the spring will go all into the dart here. So the initial energy of this system, as we look at it right now, is just elastic potential energy of the spring. So remember, that's 1/2 kx squared. The final energy is when the dart shoots out of the gun. That's all going to be kinetic energy, okay, 1/2 mv squared. So what we're going to do here is we're solving for the velocity here. So the first thing we can do is get rid of these 1/2s. They both have a 1/2, so we can just cancel those off, and we get kx squared equals mv squared. We can divide by m to get v squared equals kx squared over m. And finally, take the square root to solve for v. So v is equal to the square root of kx squared over m. K was given as 500. X is the amount, remember, x was the displacement of the spring, which we were told was 5 centimeters. That's how far we had to push in or compress the spring. So 5 centimeters, remember, we have to convert that to meters, is 0.05 meters. And also remember that is squared here, okay? And then down in the bottom is the mass of the dart, which was 10 grams. We have to convert that to kilograms. That's 0.01 kilograms because there are 1,000 grams in a kilogram. So this all comes out to be 11.2 meters per second. For our sixth example, let's take a look at one that includes friction. So this one is about a baseball player that's going to slide into second base. So a 65 kilogram baseball player running at 6 meters per second begins his slide 3 meters before reaching second base. The force of friction is 450 newtons. Does he make it to second base? So let's solve this. Again, this is one of those problems that could be solved different ways. We could find we could use Newton's laws and find the deceleration of the baseball player by using Newton's second law, F equals ma. And then we would, once we know the acceleration, we'd have to use some kinematics equations and so forth. But again, this is there's a much more direct solution here using conservation of energy. So what's happening in this example is that the baseball player has initially kinetic energy. He's running, okay? That's it. He's on the ground, so there's no potential energy, all right? So the initial energy is just 1/2 mv squared due to his running. When he slides, that energy gets converted into thermal energy by friction. Remember, whenever friction does work, it creates thermal energy. So all of this kinetic energy is going to become thermal energy. All right, so his initial kinetic energy is equal to his change in thermal energy due to the friction. So remember, the amount of thermal energy created is equal to the work done by friction. Work is force times distance. So we have the force of friction that's the F sub k, times the d is the distance that he slides, okay? Remember, he started sliding 3 meters before second base. We want to see, does he have enough energy here to slide 3 meters or more, meaning he'll make it to the base. So all we have to do is solve this equation right here for d. So that's easy. We just divide by F, the friction force. So d is equal to mv squared over 2f sub k. So his mass was 65 kilograms. His speed was 6 meters per second. We have to square that. And down here we have 2 times the friction force, which was given to us as 450 newtons. So when you do the math here on your calculator, it comes out to be 2.6 meters. Well, that's less than 3 meters. So he stops short of the base by 4 meters. In other words, he started his slide too early, and he would just come to a stop and probably get tagged out, and the fans would boo him and all that. Our next example is another one that includes not friction, but this one includes wind resistance or drag. But like friction, it's what's called a dissipative force. In other words, it creates thermal energy. It takes energy, mechanical energy, away from the system and turns it into thermal energy. So let's look at our situation here. Ryan throws a 0.6 kilogram basketball at 50 meters per second from the top of a tower of height 210 meters. So here's this tower, tall tower, right? 210 meters. Here's Ryan. He throws the ball. Notice he kind of throws it up in the air like this at 50 meters per second. So it's a projectile. And the ball ends up, crashing down here. And we're told that the ball travels 330 meters along the curved path. So the length of this blue path here, this is the trajectory of the projectile. The length of that is given as 330 meters. And we're told that the ball hits the ground at 70 meters per second. Now, this is a problem where we're actually going to include wind resistance, all right? So let's answer, this is a 5-part problem. So we're going to do quite a few things here. Question number 1 is, what is the initial energy of the ball? So we have to think about, all right, at the top of the tower here, what types of energy does the ball have? Well, it's moving at 50 meters per second, so it has kinetic energy. And of course, he's 210 meters off the ground, so it has potential energy. So the total energy of the ball is mgh, potential energy, plus 1/2 mv squared, kinetic energy. We can plug in all the numbers. Here's the mass of the ball, here's g, here's the height of the tower, a mass of the ball again, and then this is v, the velocity of the ball. These are all given to us. So we can crank all this out on our calculator, and we get 1,985 joules. Question number 2, what is the final mechanical energy of the ball? Now, we have to be careful here. If we just used conservation of energy principle, it would be tempting to just say, oh, well, the ball had 1,985 joules up here, so it must have the same down here. But that's not the case, because of the friction due to the wind resistance. So remember, final mechanical energy of the ball, that is kinetic energy and potential energy. So when the ball ends up down here, it only has kinetic energy because it has no height. So the final energy of the ball is 1/2 mv squared. Again, the mass is 0.6. We were told the final velocity of the ball was 70. So we have 1/2 times 0.6 times 70 squared is 1,470 joules. So question 3, how much mechanical energy was lost to air resistance, otherwise known as drag? Well, it started up here with 1985 joules, and it ended up down here with 1470 joules. So the change in, the delta energy is E final minus E initial. So we have the final is 1470 minus 1985. Our delta energy, our change in energy was negative 515 joules. In other words, 515 joules was converted to thermal energy. All right, that's how many joules we lost of mechanical energy, and that's how many joules was created into thermal energy. All right, so question number 4, how much work did air resistance do? Well, work, remember, this is the work energy theorem. So the work that air resistance did is equal to the change in thermal energy of this system. So, and that's equal to the 515 joules, which we solved in question number 3. Finally, in part 5, find the average force of the air resistance. Well, remember that work is equal to force times distance. So force is just equal to work divided by distance. So we know there was 515 joules. We divide that by, remember the distance that the ball traveled was 330 meters. We were given that here. So 515 divided by 330 is 1.56 newtons. Okay, so just to kind of summarize this problem, this one was a little trickier because we had 3 different types of energy involved here. We had potential energy, where it started. We had kinetic energy. And then we also, some of that energy was converted into thermal energy via drag or air resistance. But all the energy adds up, right? The total energy that it started with here, which was 1985, was equal to the total energy down here, 1470, plus the thermal energy, 515. So no energy was created or destroyed in this problem. It was just converted to different forms. Our next example says that a box of mass m slides down a frictionless hill of height h and compresses a spring with spring constant k as shown. What is the maximum displacement of the spring? So here's what's happening. We've got this box up here, mass m. It's on a hill of height h, and it's going to slide down this hill. We're going to assume there's no friction, right, which is nice. There's no thermal energy created or any. So this box slides down, and it's going to push this spring, push it in, and then probably bounce back. Now, let's think about the flow of energy here in this problem. So we start out at the top with just potential energy due to gravity. So that's our U sub G. As the box slides down the hill, that potential energy is being converted into kinetic energy. In fact, when the box reaches the bottom of the hill right here before it hits the spring, all of that potential energy has been converted into kinetic energy. But then the box slams into this spring, and all that kinetic energy gets converted into elastic potential energy, the US, which S is for spring. So the spring compresses until it gets to its maximum compression. At that point, the kinetic energy is 0 because the object stops, the box stops, and all the energy is stored in the spring. So at that point, we're going to figure out how far did the spring actually compress. So, it's a fairly, seems like a kind of a complicated situation here with all this going on, but it's actually a pretty simple problem to solve because the initial energy here is just mgh, potential energy. The final energy here is all elastic potential energy, 1/2 kx squared. So we just set these two equal to each other, and our goal is to solve for x. So, this is the physics right here. The rest is just 2 steps of math. So how do we solve for x? Well, x squared, we can multiply both sides by 2. We can divide by k. That's what I did here. And then finally, just take the square root of all this. And x is equal to the square root of 2 mgh divided by k. And this problem doesn't have any numbers, so this is our solution. If we were given numbers, we would obviously be plugging those into the equation there to figure that out. But this is what we were looking for. So hopefully at this point you have a pretty good understanding and feel of how to use conservation of energy. It's a different way of looking at a problem. In the past, we were kind of looking at the dynamics with forces, thinking about, what's pushing and pulling, what are the net forces and all that. Now, with our energy, we have a different way of looking at situations. We can just think in terms of energy, and that's often the easiest way to solve problems. So let's do a little conceptual quiz here. We've got 2 roller coasters here. They both are at the same height, and both roller coasters are starting at rest at the top. Roller coaster A, you can see, is really steep, and the roller coaster is going to glide down this really steep hill. Roller coaster B, with the same height, is less steep. It's a much longer hill, and it also has a loop here where you're going to loop upside down until you finally reach the bottom. So the first question is, which roller coaster will be going faster at the bottom? And the second question, which roller coaster will get to the bottom first? So go ahead and pause the video and think about this and see if you can answer these questions. And be sure to use your knowledge of conservation of energy. Okay, well, to answer the first question, the answer is neither. It's a tie. And the reason for this is conservation of energy. Both roller coasters start with the same amount of energy at the top. They're both at rest and they're both at the same height. When they get to the bottom, due to conservation of energy, they will both have the same energy at the bottom. So since all of the energy is kinetic energy at the bottom, that just depends on the speed of the roller coaster. So since the energies are the same, the speeds of the roller coaster are the same. So A and B are both going equally fast at the bottom. Now, which roller coaster will get to the bottom first? Well, in this case, A will get to the bottom first. A is going to accelerate faster. It has a shorter distance to travel. B will take more time. It's going to go around this loop, right, which is going to take some time. And so by the time it gets to the bottom, even though it's going just as fast as A, it took longer for it to reach that final speed. The last few examples here I'm going to show you are just a little bit more challenging since they involve some different ideas here. Let's take a look at this one here. It says a solid ball rolls down a ramp with height h. What is the ball's speed at the bottom? So the ball starts up here and it rolls down, and it's going to pick up speed, accelerate, and we're going to try to figure out how fast it's going at the bottom. So we're going to solve this using conservation of energy. So the initial energy of the ball, it's starting at rest, so all it has is potential energy, mgh. The trick to this problem is that at the bottom, the ball has, no more potential energy, right? It's all kinetic. However, it has two types of kinetic energy. It has translational kinetic energy, 1/2 mv squared, and it has rotational kinetic energy, 1/2 I omega squared. Remember, we learned about rotational kinetic energy in one of the earlier parts of this chapter's lecture. And the velocity of the ball and its angular velocity, omega, are related by omega equals v over r. So there's a couple things we have to do here. The first thing is this I. Remember, this is the rotational inertia. So we have to look this up in a table. Going back to chapter 7, looking up a solid sphere. All right, it has a rotational inertia of 2/5 mr squared. And then the omega here, we're going to replace with v over r, and that is squared as well. So what happens here is this r squared cancels out with this r squared. Remember, this whole thing is squared. So the r's cancel. And also this 2 cancels with that 2. So we end up, oh, and one more thing, they all terms have m. So we can cancel out all the m's. So it comes down to a fairly simplified result here. GH equals 1/2 v squared plus 1/5 v squared. So we can add these two terms together. They're both v squared. To do that, we use least common denominators, right? 1/2 is the same as 5/10, and 1/5 is the same as 2/10. So 5/10 plus 2/10 is 7/10. So we have GH is equal to 7/10 v squared. V squared is therefore equal to 10 over 7 times GH. And finally, we take the square root to get our answer. The speed of the ball is the square root of 10 over 7 times G times H, where H is the height of the ramp. Here's another semi-challenging problem that involves rotation as well. So in this one, a flagpole of length L breaks at its base and falls over. How fast is the tip of the flagpole moving when it hits the ground? All right, so here is the initial flagpole standing up like this, and it snaps off down here, and it falls like this and ends up on the ground here. So interestingly, this is another great case where we can use conservation of energy to find the solution in just a couple steps. The key, as always, is identifying what types of energy are present, initially and finally. So the initial position here, the flagpole is not moving, so it only has potential energy. And this is a little tricky because you're thinking, well, the flagpole is on the ground, right? So it doesn't have any potential energy. But that's not true. Remember, the flagpole has mass that extends all the way to the top. So the way to figure out the potential energy of the flagpole here, we use the center of mass of the flagpole. So we can model this as if all of the mass of the flagpole were at its center of mass. And remember, the center of mass for something like a flagpole is just halfway across the flagpole. So if the length is L, then the cm is at L over 2. That's the height. So our height here, our h in mgh, is equal to L over 2. So you can see I've substituted that in here. Now, what about on the right side? We're talking about the final energy of this flagpole. Well, as it falls, right before it hits, it doesn't have any potential energy left because the whole flagpole is basically at the ground. What it has is rotational kinetic energy, because this whole thing, you can think of it as rotating about the pivot point here at the bottom. So we need to figure out, remember the rotational kinetic energy is 1/2 I omega squared. We need to look up a flagpole or a rod that's rotating about its end, and the I, or rotational inertia for that, from the table, again, from chapter 7, is 1/3 ml squared, where L is the length. The other thing here, again, the omega, which is the rotational velocity of this flagpole, is equal to V over L. You can think of L here, the length of the flagpole, as sort of like the radius of this circle. And remember that omega is equal to V over R. So we can plug that in here. And again, what happens is this L squared cancels with this L squared, just like the last problem, very similar. What else do we have here? We have M in both terms. Those cancel out. Also, this 2 down here cancels with this 2 here. We can cross out the 1/2. So we end up with GL equals 1/3 V squared. So V squared is equal to 3GL. And taking the square root, here's our final answer. It's actually a very simple expression. The speed of the tip of this flagpole is equal to the square root of 3GL, where L is the length of the flagpole. In this next example, this is another one involving rotation. And this is similar to a problem that we saw before when we looked at rotational dynamics in, I guess it would be chapter 7. Now we're gonna approach this problem from an energy perspective. So we've got a hanging mass down here, 0.4 kilograms, is attached to a string wrapped around this cylinder like this. How fast is the small mass going after it falls 1 meter when released from rest? So notice we're given some information about the cylinder. It has a radius of 3 centimeters. It has a mass of 1.3 kilograms. So we can kind of see what's going to happen here. Initially, we have potential energy due to this hanging mass because it's off the ground. When this thing, after this thing falls, obviously some of that energy is going to be converted into rotational kinetic energy. So let's take a look at how to do this. So the initial energy is mgh for the hanging mass. The final energy is the kinetic energy of the falling mass plus the rotational kinetic energy of the rotating cylinder. And again, this V and this omega are related by omega is equal to V over R. So once again, we have to look up in the table, what is the I? What is a rotational inertia for a solid cylinder? Well, it's 1/2 mr squared. So that's from the table again in chapter 7. And also this omega here, we're going to replace with V over R. So that's what's in the parentheses here. The R's cancel, as we've seen several times now. And what we can do here is we're going to solve for V. All right, so we've got V in this term, we've got V in this term. So let's factor out the V squared. And so we have V squared, and in parentheses, we have the 1/2 m, which is here, and then we have the 1/4 uppercase M. All right, remember, little m is for the hanging mass, big M is for the cylinder. And on the other side, we have mgh here. So finally, to solve for v squared, we have to divide by all the stuff in the parentheses here. So that's shown here. And to get v, we take the square root of that entire expression. And so then the final step is just to plug in all our numbers. I'll let you go through those. All those values were given to us on the last slide in the problem. And this comes out to be I should mention that the height here, we're letting it fall 1 meter. So that's where that 1 comes from there. The final velocity then is 2.73 meters per second. So here's our final example on conservation of energy and our final example from this chapter. So a basketball rolls across the floor at 2 meters per second and approaches a ramp. What height h does the ball reach on the ramp? So this is another good problem for conservation of energy. So we've got the initial basketball here is rolling. So it has 1/2 mv squared. This is the translational kinetic energy because it's moving, plus the fact that it's rolling means it's rotating. So it has rotational kinetic energy, 1/2 I omega squared. And again, omega is equal to v over r. Now, when the ball rolls up the ramp, it comes to a stop before it rolls back down. So at its stopping point here, that's the maximum height, which we're going to solve for. And at this point right here, since it's stopped, it's not rotating either, so omega is 0. It has no more kinetic energy. It's all potential energy. So the final energy of the system is just mgh of the ball. So again, we have to look up I for a basketball. Now, a basketball is not a solid ball. It's hollow. It's a hollow spherical shell or a hollow sphere. And it has a rotational inertia in the table given by 2/3 mr squared. Omega here, again, I've substituted v over r. And, once again, the r's cancel. The r squareds cancel. And we end up in the m's also cancel. All the terms have an m in it. So we end up with this relationship here. Now we've got 1/2 v squared plus 1/3 v squared. We can add these together by using least common denominator. So 1/2 is the same as 3/6. 1/3 is the same as 2/6. So 3/6 plus 2/6 is, of course, 5/6. So I have GH is equal to 5/6 v squared. Therefore, H is equal to, let's see, did I make an, boy, I might have made an error here. Oh, no, I'm okay. I have to just divide by G. I'm good. So H is equal to 5v squared over 6g. And finally, we can plug in our numbers. V is equal to 2, and G is 9.8, which gives us a total height, final height of 0.34 meters. So that, my friends, is the end of this chapter. This was, I know, a long part of the video, but conservation of energy is an important topic, and I want to make sure you guys get a good understanding of this before we move on to the next chapter. Until then, I'll see you then.